Welcome to this lecture of abstract algebra. In this lecture, we shall study the proof of Zassenhaus Lemma. This is an important lemma that is required for the proof of Schrie refinement theorem, which talks about the equivalence of refinements of any two normal series of a group. The Zassenhaus Lemma states that if we have a group G and A is normal in A star and B is normal in B star such that all A star, B and B star are the subgroups of G, then there is an isomorphism like this, which is defined here. If we look into this expression of isomorphism, this is obviously a group isomorphism. In order to make this group isomorphism well defined, we must have the group in the denominator of this expression on the left hand side is a normal subgroup of the numerator on this left hand side. And similarly, the denominator, that is b into b star intersection a, this must be a normal subgroup of b into b star intersection a star. So before proceeding towards proving the isomorphism of these two groups, we must show that the denominator of these expressions is a normal subgroup in the numerator of this expression. So our first step to prove is to show that a into a star intersection b is a normal subgroup of a into a star intersection b star. But here we can obviously see that this a is always normal than a, so we are only required to show a star intersection b is a normal subgroup of a star intersection b star. So this shall be our first step. First we show a star intersection b is a normal subgroup of a star intersection b star. For this we choose x belonging to a star intersection b star and we choose C belonging to A star intersection B. Then we have to show that X inverse belongs to A star intersection B. So that is what we have to show. So we show this X inverse belongs to A star intersection B. So this is our requirement. Now in order to do this, what we do, so from this expression we have this x belongs to a star, and from here c belongs to a star intersection b gives that c belongs to also a star. So this implies x inverse, this belongs to a star. And again, from here in this expression we have x belongs to b star, and from here we have c belongs to b. Now this implies x inverse, this belongs to b star. This belongs to b in fact because this b is a normal subgroup of b star. So first we again revise this. When we have this x belongs to a star and c belongs to a star, so any composition of these two elements will belong to a star. And now b is a normal subgroup of b star, so therefore for every x in b star and c in b, we will have x inverse belongs to b. So now combining these two, hence we obtain this x inverse, this belongs to a star intersection b. So we have shown the group A star intersection B is a normal subgroup of A star intersection B star. So therefore, this A star intersection B is a normal subgroup of A star intersection B star. Now at this stage, if we interchange the roles of A and B, we can show that B star intersection A is also a normal subgroup of B star intersection A star. So on similar lines, we have B star intersection A is a normal subgroup of B star intersection A star. So we have shown the left hand side denominator is normal in the numerator, and similarly the denominator on the right hand side of this expression is a normal subgroup of the expression in the numerator. So this gives us, hence if we define D, hence the set that we shall name as D, which is equal to A star intersection B into B star intersection A. Now this is also a normal subgroup of A star intersection B star. Now this D is normal in this A star intersection B star because it is generated by two normal subgroups, because D is generated by two normal subgroups. Our next step is to show that there is an isomorphism. So next we show there is an isomorphism from A into A star intersection B star by A into A star intersection B to A star intersection B star by D, where this D is defined as above. So this is A star intersection B star by A star intersection B into A intersection B star. Now, in order to show this isomorphism, we must define a mapping which is a homomorphism and is a bijective map. For this, define a map pi from A into A star intersection B star into A star intersection B star by D, defined by pi of Ax is equal to dx, where A belongs to A and x belongs to A star intersection B star. So this is how we define a map. We take an element from A into A star intersection B star, where A is an element of A, and we choose a representative of A star intersection B star as x. Then this is defined as dx. We show this is a 1-1 onto homomorphism so that we prove an isomorphism. So then the first step of our mapping must be that this mapping is a well-defined map. So we first show pi is well-defined. For this, let Ax is equal to A dash x dash, where A and A dash are elements of A and x comma x dash, they are elements of A star intersection B star. So then when we pre-multiply this expression by A dash inverse, we obtain A dash inverse into A. Now on the right, we multiply this expression by x inverse, so this becomes x dash into x inverse. So this expression is obtained by pre-multiplying this expression by A dash inverse and post-multiplying it by x inverse. Now if we analyze this expression, now on this left-hand side we have A and A dash, they are the elements of A. So this left-hand side belongs to A, and the right hand side expression x dash and x, they are both elements of A star intersection B star, so therefore this expression belongs to A star intersection B star. Now if we merge them together, so we must have this element belongs to A into A star intersection B star. But now here at this stage, A is a normal subgroup of A star, so we must have this is equal to A intersection B star. This is because we have this A is a normal subgroup of A star. So when A is contained in A star, so therefore A intersection A star is equal to A, and then we have here B star. Now from this we obtain, so this implies this x dash x inverse, this actually now as this belongs to A intersection B star, so therefore this is, and this set is contained in A intersection B star into A star intersection B. But now this expression on the right hand side, this is equal to D. So this gives us x dash x inverse belongs to D. So this means this D x dash x inverse, this is equal to D, and this further implies D x dash is equal to dx. But this is the definition of, the left hand side is the definition of pi of ax dash in fact, and the right hand side is an expression for pi of ax. So that means if we choose two elements ax equal to a dash x dash, we obtain pi of ax dash is equal to pi of ax. So therefore the mapping pi is a well-defined mapping. Now let's proceed toward the second step, proving that this pi is a homomorphism. So next, this phi is a homomorphism. For this, so again let ax and a dash x dash, suppose these are two elements of A into A star intersection B star, where again A and A dash, they are elements of A, and x dash, they are elements of A star intersection B star. Then let's evaluate this pi of ax a dash x dash. Now we can write this expression as pi of a x a dash. Now here we include x inverse x into x dash, because x inverse x is equal identity. So therefore this is equal to pi of a x a dash x inverse, and we write it like this, x into x dash, because these are all the elements of a group, so they are associative, they are all the elements of a group G, and that G satisfies the associative property. Now here we evaluate this expression ax a dash x inverse here. Now for this a belongs to a, and also x a dash x inverse, this also belongs to a because a is a normal subgroup of a star, and here x was an element of a star, a dash is an element of a, so therefore this element belongs to a. So this implies a x a dash x inverse, this is an element of a. So therefore this first expression is an element of a. So we can write this as phi of a, suppose double dash x x dash. So we can actually write here, so this is equal to a double dash belongs to a. Now here where this a double dash is equal to a x a dash x inverse, which is an element of a. Now let's recall the definition of pi of a dash x. It is equal to now d x x dash, and at this stage we can write this is equal to d x x dash. Now here, because this this must be equal to d because it's a subgroup, and now this is equal to d x dash. So the reason for this step is because this dx is equal to xt, and we have used this dx to be equal to xt. Now this dx, this is equal to phi of ax, and this dx dash, this is equal to phi of a dash x dash. So thus we have proven that pi is a homomorphism. So this implies pi is a homomorphism. Now our third step is this pi is also surjective, since for every dx which belongs to a star intersection b star by d, we have pi of ax is equal to dx for some a belongs to a and x belongs to a star intersection b star. So pi is in fact trivially surjective. So thus pi is an onto homomorphism. Thus pi is an onto homomorphism. Therefore, by fundamental theorem of homomorphism, we obtain this A into A star intersection B star by kernel of pi. This is isomorphic to A star intersection B star by D. So we have this isomorphism. Now we evaluate what is this kernel of pi in this evaluation or definition of pi. So finally, this kernel of pi, this is equal to set of elements ax such that pi of ax is equal to d. Now pi of ax must be equal to d because d is the identity of a star intersection b star divided by d. So this is defined as ax such that now phi of ax, this is defined as dx, is equal to d. So therefore kernel of pi is the set of elements ax such that x belongs to d. Now here in this definition we have pi contains all those elements ax where a belongs to a and x belongs to a star intersection b star. So therefore pi kernel of pi contains elements of the group a into a star intersection b star for which the element of a star intersection b star is precisely the element of d. So this means this gives this kernel of pi. This is the element of this form, element of the form AD. Now A is an element of A, and here X happens to be an element of D in this definition. Now this is equal to A. Now let's replace the definition of D. So D is equal to A star intersection B into A intersection B star. Now we can also write this as this is A into A intersection B star into A star intersection B. Now if we look into this expression A intersection B star, now this expression A intersection B star, this is a proper subset of A. So therefore, this is equal to A into A star intersection B. The reason for this is because this A intersection B star, this is contained in A, and and we know that if we have like H and K are two subgroups of any group, this must be equal to K if H is inside K. So that is the property we are using here. So A intersection B star is a proper subset of A. So therefore, the product of these two groups is actually the group A. And now here we replace the expression A star intersection B again here. So this means, hence, we have this A star. Hence, we have A into A star intersection B star by kernel, and now we have shown the kernel is equal to A into A star intersection B. Now this is isomorphic to A star intersection B star upon D, but here we replace the value of D. It is A star intersection B into A intersection B star. So we have shown this isomorphism. Now interchanging the roles of A and B, interchanging the roles of A and B, and in fact also for A star and B star, we obtain, now here wherever we have A, we will replace it by B, so we will get B into B star intersection A star by B into B star intersection A. This is isomorphic to B star intersection A star by B star intersection A into B intersection A star. Now let's name this as equation number 1, and let's name this as equation number 2. Now if we compare the equations first and second, we can see that the right hand side is exactly identical in equations first and equation second. So therefore the left hand sides must be isomorphic. So we write combining equations first and second, we obtain A into A star intersection B star by A into A star intersection B. This is isomorphic to B into B star intersection A star by B into B star intersection A. So this completes the proof of Zassenhaus Lemma.